Hello class! So today, here in Statics of Rigid Bodies, we are now going to discuss our 17th lesson, which is the Introduction to Moment of Inertia. So for this lesson, students must be able to solve the moment of inertia of common geometric shapes. So let's start our discussion. Okay, so let's define first what is a moment of inertia. So the moment of inertia or of area is sometimes called the second moment of area because of each differential area multiplied by its moment arm gives the moment of area. When multiplied a second time by its moment arm, it gives the moment of inertia. So as you can recall in our discussion about centroids, okay, so this formula are the formulas that we are using, right, in solving for the x and y coordinate of a centroid. Okay, so if you're going to recall, I've mentioned in our discussion that this ax bar or ay bar, okay, this is called moment of area, right? So this is also called moment of area because we are taking moment, no, of this area wherein the moment arm will be x bar, and in this case, it will be y bar, no, the moment arm. Okay, so if we are going to multiply, an area, okay, by a moment arm twice, no, so that will be the moment of inertia. So as you can see here, no, so this is integral of y squared dA, no, so this is actually equivalent to this, right? So in this case, the differential area here is multiplied um uh by its moment arm twice, right? So this integral of y squared dA, this is actually moment of inertia with respect to x, no, or with respect to the x-axis, or moment of inertia about the x-axis, no. So the moment of inertia about the x-axis, this is written this way. Okay, so this is I sub x. So I means moment of inertia, and the subscript here, this is the reference axis where we measure the moment of inertia. Okay, so same here, no. So this integral of x squared dA, no. So this is equivalent to this, but the difference is that the differential area here, no, it is multiplied by the moment arm x twice. Okay, so this is now the moment of inertia about the y-axis. Okay, so this is written, no, as I sub y, no. So moment of inertia with respect to the y-axis. So that's how we measure moment of inertia, ha? So there's always a reference axis, no, where we measure the moment of inertia. Okay, so in this case, no, so don't get confused, no, with this. So if you are measuring the moment of inertia about the x-axis, the moment arm will be y, right? Because the moment arm will, from the x-axis, it will be measured vertically, so that will be y. Okay, now for moment of inertia about the y-axis, the moment arm, since you are going to measure the moment of inertia from the y-axis, the moment arm will be measured horizontally, so that will be x. Okay, so that's why for moment of inertia about x-axis, that will be integral of y squared dA, while for moment of inertia about the y-axis, that will be integral of x squared dA. Okay. Okay, so let's solve sample problems now. Determine the moment of inertia for a rectangle of base B and depth h with respect to letter A, the x-axis, letter B, the y-axis, and letter C, a centroidal axis parallel to the x-axis. So we are going to determine here the moment of inertia for a rectangle. Okay, so actually there's already an established moment of inertia, no, for rectangle, but this is actually the derivation, okay, of that established moment of inertia. So we are going to determine the moment of inertia for a rectangle, no, about the x-axis, about the y-axis, and about a centroidal axis parallel to the x-axis. So a centroidal axis parallel to the x-axis, this is the x-centroidal axis, no. So this is the horizontal axis, okay, that passes through the centroid. Okay, so that is called that is called centroidal axis. Okay, so let's solve this. Okay, so again, for this problem, we are going to find the moment of inertia with respect to the x-axis, y-axis, and the centroidal axis parallel to the x-axis, or simply the x-centroidal axis, no? Okay, so for our solution, okay, so let's say this is the rectangle. No, so the rectangle, no, as mentioned in the problem, it has base B and height h. No, so this will be base B and this will be height h. Okay, so in this case, for the first one, no, we are going to measure the moment of inertia about the x-axis. So the x-axis will be our reference point or reference axis. No, so using our formula, no, for the moment of inertia about the x-axis, it will be integral of y squared dA. No, so we are going to construct here a rectangular strip. No, so we will draw the rectangular strip here. No, this way. Okay, so since this is the orientation of our rectangular strip, no, so we will name the longer side, no, as x, no, so since this is parallel, no, to the x-axis, this side, no, and then the shorter side, which is very thin, no, we will name it as dy, no, so this is differential y. Okay, so we are going to use our formula here, no, so for this rectangular strip, no, so its centroid, no, is actually located here, no, so the moment arm, no, so the moment arm of this rectangular strip, no, from the x-axis, it will be y, no, so this will be y. Okay, so we're going to apply now this formula. So we will run our strip, no, from here to here at this point, no, we will run our rectangular strip. So its limit, no, it will be from 0 to h, no, so that will be our limit, and then y squared dA. So in this case, we are going to solve for our differential area. So this is our differential area. So this is rectangle, no? So its area will be base times height. So this will just be simply x dy. Okay, so in this case, we are going to integrate, no? Integrate this with respect to y. No? So meaning to say, all functions here should be expressed in y, no? In function of y. Okay, so in this case, this x, no, we will express this, no, into its equivalent equation, no. Okay, so in this case, this is ano, no, this is x. Okay, so this is the function of x. So this is where our rectangular strip touches, no. So we need this equation, the equation of this. So the equation of this, okay, this is actually x is equal to b, no. So we will rewrite x, no, into its equivalent function here, which is b. Okay, so b is a constant, so there will be no problem for that. If that's a constant, no, we can just integrate y squared dy, no, and just factor out this constant b. Okay, so in this case, no, so integrating y squared dy from 0 to h, we just factored out b here, no, so that will just be y cubed over 3, no, and we will evaluate this from 0 to h, so we will substitute the upper limit h, no, to variable y, minus we substitute the lower limit, which is 0, to variable y, which that will become 0 lang, no, so we will not include that anymore. So this will just become bh cubed over 3. So this is now the moment of inertia about the x-axis. So this is bh cubed over 3. So you will actually see this, no, in our table for the value of moment of inertia of some common geometric shapes, no. So if we measure the moment of inertia of a rectangle wherein the x-axis is at its base, no, so automatically its moment of inertia about that axis is bh cubed over 3. Okay, so let's proceed now to letter B. So that will be moment of inertia about the y-axis. Okay, so for letter B, no, so we are going to use this formula. So this is moment of inertia about the y-axis. So this will be equal to integral of x squared dA. So again, since we are measuring the moment of inertia from the y-axis, our moment arm will be x, ha. So it will be measured horizontally from the y-axis. Okay, so that's why the moment arm here is x. Okay, so this is our rectangle. No, so this is base B and height h. So to solve for the moment of inertia, we are going to construct a rectangular strip here. So for our rectangular strip, the longer side, we will name it as y. No? So since this is parallel, no, to the y-axis. Now, the shorter side, no, so again, that shorter side is so thin. Okay, so we will name it as dx, no, since this is parallel to the x-axis. Now, we are going to use our formula here. Okay, so we will run this rectangular strip, no, from here to here. Okay, so our limit here will be from 0 to b. Okay, so that will be our limit, then x squared dA. Okay, so for our dA, so this is the differential area, so we will solve for the area of this rectangular strip. So since this is a rectangle, its area will just be base times height, so that will just be y dx. Now, we are going to integrate this with respect to x. So, this variable y, we should express this in terms of x, no? So, in this case, the equivalent function for y, no? So, since our rectangular strip is touching this line, okay, so we need the equation of this line. So, the equation of this line is actually y is equal to h. No, so this is y is equal to h. So we will express y, no, as h, no, since that is the equivalent equation. Okay, so h is a constant. Okay, so since h is a constant, no, there will be no problem here. We can just factor that out here and then integrate x squared dx. Okay, so integrating x squared dx, so that will just be x cubed over 3. So we will evaluate this from 0 to b. Okay, so substituting the upper and lower limits, no, to variable x, so that will just be b cube over 3, no, minus 0 cube over 3. So that will just be 0, no, yung 0 cube over 3. So we will not include that, no, anymore here. So this will just become hb cube over 3. So this will now be the answer for moment of inertia about the y-axis. Okay, so as you can see here, no, so this is just from our letter A, no, so that is moment of inertia about the x-axis, that is hb cube, no, over 12. So in this case, this is bh cube over 12, no, from letter A. Now here, this is hb cube over 3. So as you can notice, they are just interchange, because if we are going to use y-axis as the reference axis, actually, no, if we take this as the x-axis, no, the y-axis, if we change the orientation, let's say this y-axis is the x-axis, no, so the base here will be this, no, and the height will be this. That's why it's just interchange here, no, h and b cube, no. Anyway, so memorize also this, no, because you will also see this in our table, no, with values of the moment of inertia, no, for some common geometric figure. So you will see this in the tables. Okay, now for letter C, this is moment of inertia about a centroidal axis parallel to the x-axis. So this is just the x-centroidal axis. So this is the axis that passes through the centroid, okay, of the area. No? So in this case, this is a rectangle. Okay, so in this case, this is a rectangle. So the x-centroidal axis will be this axis. Okay, so this is the x-axis that passes through the centroid, no, of this geometric shape. Okay, so in this case, we are going to use this formula. Okay, so this is the moment of inertia, no, with respect to the x-centroidal axis. So for x-centroidal axis, we denote that, no, as x sub o, no, for y centroidal axis, no, that is y sub o. So x sub o means x centroidal axis, y sub o means y centroidal axis. Okay, so this will just be integral of y squared dA, since this is x axis, no, so this is still x axis, so its moment arm will be measured vertically, no, the moment arm of the area, so that will still be just y, no. So if you are going to construct here a rectangular strip, no, so this is our rectangular strip. Okay, so so if this is the rectangular strip, so we will name the longer side as x and the shorter side as dy. Okay, so the centroid of this rectangle will be somewhere here, no, of this rectangular strip, ha. So its moment arm will be this, no, so this is y, so this is denoted as y, no, the moment arm. So we are going to use our formula, no, so using our formula, so our rectangular strip, it will run from here to here, but we can actually then we can actually just run our rectangular strip from the reference x-axis, which is the x-centroidal axis, up to this point, no? So this will just be 0 to h over 2, no? So this is just half of h, no? So we can do that, and then we just multiply by 2, since the area here above is just equal to the area here below, no? So we can just multiply that by 2, no? So we will use that limit, no, from 0 to h over 2, and then we just multiply by 2. Now, our dA, our differential area, so that will just be x dy. So we will express x in terms of y, since we will integrate this with respect to y. Okay, so the equivalent equation for x, no, so we need the line, no, where our rectangular strip touches, no? So this line, no, touches our, or yeah, this is the line that where this rectangular strip is touching, no? So we are going to know this this rectangular strip, this line, no? So the equation of this line is actually x equal to b, no? So b is a constant, no? So in this case, we will have no problem if we integrate y squared dy. We can just factor out b, no? So integrating y squared dy, that will just be y cubed over 3, no? So our limit will be from 0 to h over 2, so we will evaluate this, no, from 0 to h over 2. So substituting the upper limit first to the variable y, okay, and then we subtract, no, we substitute the lower limit, which is 0 to y cube also, so that will just become 0, no? So we will not include that anymore. So in this case, this will become 2b times h over 2 cube over 3. So simplifying this, no, so this is actually bh cube over this is over 12, no? So this is bh cube over 12. So in this case, this is also no, already established, no? So this is the derivation, okay, of that established moment of inertia. So again, this is moment of inertia with respect to the x-centroidal axis, no? So be familiarized already, no, with this values. Okay. And now, these are already the established moment of inertia of some common geometric figure. So, as you can see in the table, no, so here you can see Ix bar here and Iy bar, then Ix and then Iy. So, Ix bar, no, means this is the x-centroidal moment of inertia. So you can write x-centroidal moment of inertia either Ix bar or I sub x sub O. No, so they are just they are just the same. No, so also for Iy bar, so you can also write Iy bar as I sub y sub O. No, so these are the x and y centroidal moment of inertias. Okay, so our x and y centroidal axis, no, if this is the geometric figure, no, so this is a rectangle, so its centroid is located somewhere here at this point, no, so this is at the center of the rectangle, no, so the x and y centroidal axis, no, will pass through that point, no, so this will be this will be the location, no, of the x-centroidal axis, no, and this will be the location of the y-centroidal axis. Now, if we are going to measure the moment of inertia of this rectangle, no, from this axis, no, so this is x-centroidal axis, no, so that will be bh cubed over 12. So we actually solved this, no, already from the sample problem that we solved, no, in letter C. So this is that is actually the derivation, no, that is the derivation of this value, no. So this is bh cubed over 12. Now for Iy bar, no, or the y centroidal moment of inertia, so the moment of inertia here is measured, no, from this y centroidal axis. So this is hb cubed over 12. So if you can see here, no, H and B here are just interchanged, no, from here, no. So that's how we do it. Okay, so now also for Ix, no, so this is the moment of inertia with respect to the x-axis. So in this case, the x-axis is at the base of the rectangle. So this is the base of the rectangle, or this is the x-axis, no. So the moment of inertia measured from this axis, no, of this rectangle will be bh cubed over 3. So we already derived this also, no, from our sample problem, no, that we solve, no. So that will be the moment of inertia, no, with respect to the x-axis if the x-axis is at the base, no. Now for the moment of inertia with respect to the y-axis, so if the y-axis is located here, no, at this side of the rectangle, so its value will be hb cubed over 3. So again, b and h here are just interchange, no, since this is the axis, no, that will be that will be used as the reference. Okay, so you have to remember that always that if you are going to solve for moment of inertia, you need a reference axis. No, so in this case, these are the reference axes, no, for this established moment of inertia. Okay, so also for a triangle, no, so for this established moment of inertia, you can also solve this, no, using integration. No, so that's how we derive this, no, but we will not derive it here anymore, no. So these are the moment of inertias, no, for a triangle. So as we know, the centroid of a triangle is located somewhere here, no. So the axis that will pass through that point will be the x and y centroidal axis, no. So if you're going to measure the moment of inertia of this triangle, no, about the x centroidal axis, no, its value will be bh cubed over 36. So you can confirm this, you can confirm this value by using integration, no. You can do that, no. Okay, and also for iy bar, or the y centroidal moment of inertia, so its moment of inertia will be measured from this y centroidal axis, no. So if you do that, if you measure the moment of inertia about this axis, so this will be hb cubed over 36. So the b and h here are also just interchange. Also for ix, no, so this is the moment of inertia measured from the x-axis. So in this case, the x-axis is at here, no. So this is the x-axis, no. So the value for that is bh cubed over 12, no. And for iy, or the moment of inertia with respect to the y-axis, so the y-axis here is located here, no. So the value for that will be hb cubed over 12. Okay, so you have to memorize this, okay. So we will use these values, no, for our next problems, no. So you have to memorize this moment of inertias. Okay, so now for circle, no, so there's also already an established moment of inertia for a circle, no. So for the moment of inertia about the x and y centroidal axis of the circle, no, so its x and y centroidal axis will be located somewhere here. Of course, it will pass through the center, no, or the centroid of the circle, which is at this point, no. So if you're going to measure the moment of inertia with respect to the x centroidal axis, it will be pi r to the fourth over 4. Of course, this is a circle. So if you measure the moment of inertia with respect to the y centroidal axis, it will just be the same. So that will also be pi r to the fourth over 4. Okay, now for a semicircle, so this is our semicircle. No, so this is the orientation, no, of the semicircle for this for this established centroidal moment of inertias. Okay, so for this semicircle, its centroid will be somewhere here. So its x centroidal axis will be here, and the y centroidal axis will be here. So if you are going to measure the x centroidal moment of inertia, no, so it will be measured from this axis, no, so it will be pi r to the fourth over 8. No, now for the y centroidal moment of inertia, of course, it will be different because this is not a circle. No, it will be different if we measure the moment of inertia from the y centroidal axis. So it will be 0.11 r to the fourth. So as you can see here in this table, no, we did not include here the moment of inertia with respect to this x-axis and this y-axis, right? So we did not include that here because there's another way, no? There's another way that we can solve for that, no? Easier, no? By just using this established centroidal moment of inertia, no? So that, it cannot be, it will not be too much for you that you have a lot to memorize, no? So there's another method, no, to solve that, no, without memorizing that. Okay, so we will just use this, no, the x and y centroidal moment of inertia to solve for the moment of inertia with respect to this x-axis and this y-axis. So we will discuss that in our no, next topic or succeeding slides, no. Okay, also for the moment of inertia for a quarter circle, no? So this is our quarter circle. So this is the orientation, ha? Okay, of the quarter circle for these values, ha? Okay, so if you're going to measure the x and y centroidal moment of inertia, so the centroid of this quarter circle will be located somewhere here. So this will be the x and y centroidal axis, no? So its x centroidal moment of inertia, no, it will be measured from this axis. It will be 0.055 r to the fourth. So it will just be the same actually, no, for iy bar, because it will just be the same if we measure our moment of inertia from here, no, and also from here, no. So it will just be the same. Okay, so you have to memorize this, ha, this established moment of inertias. Now let's proceed to polar moment of inertia. So the moment of inertia for an area relative to a line or axis perpendicular to the plane of the area is called the polar moment of inertia and is denoted by the symbol J. So this moment of inertia, now this moment of inertia or polar moment of inertia, this is measured, no, its reference axis, no, will be the axis perpendicular to the plane, no. So this is the axis perpendicular to the screen, no. So this is the z-axis, no. So this is the axis that is perpendicular, ha, to the plane. Okay, so that will be the reference axis, no, in measuring the moment of inertia, no, for polar moment of inertia. Okay, so this will be the formula for that. So this is jz. So jz, this will be the notation, no, for polar moment of inertia. So the reference axis for this, again, no, this is z, no. So this is the axis perpendicular, no, to the plane, no. Okay, so this will just be equal to ix plus iy. So ix and iy here, these are the moment of inertia with respect to the x and y axis, no. Okay, so we actually derived this from here, no. So let's say we have here this area. Okay, so if you're going to get the differential area of this area, so it will be this no, differential area. So if you're going to measure the moment of inertia with respect to the x-axis, its moment arm will be this, no. This is y, no. Now for moment of inertia with respect to the y-axis, no, its moment arm will be this, no. So this is x. Now if you're going to measure the moment of inertia with respect to the axis that is perpendicular, no, this is the axis, no, that that is backward or forward, no. So that is the z-axis. So the z-axis, that will be the reference axis. So if that is the reference axis, no, so the moment arm here will be this this length, no, or this distance, no, which is r. We will name it as r, no. So we can solve actually that no, that moment arm, this r, no. So from Pythagorean theorem, no, so we can use this triangle wherein this is y, this is x, no, and this is r. So r is the hypotenuse, no. So this will just be equivalent to x squared plus y squared, right? The x and y the this r squared, no, using Pythagorean theorem nga. Okay, so if you are going to distribute this, no, so this will become integral of x squared dA, which sounds familiar to you, right? Integral of x squared dA is actually iy, right? And the integral of y squared dA, no, that is also familiar to you. That is actually ix, no. So meaning to say, no, this is just really equivalent, no, to ix plus iy, no. So this is the formula, ha, that we're going to use here for polar moment of inertia. So, the example here is that, let's say we have this rectangle. Okay, so if we are going to measure, no, the moment of inertia with respect to the axis, no, that is located, no, or perpendicular to one of the corners, no, of this rectangle. So let's say the corner that we're going to consider is here at this corner. No, so the axis that is perpendicular to this corner is the x-axis. So if you're going to measure the polar moment of inertia of this area, no, so we will just need to solve for the moment of inertia of the x-axis. This is the x-axis. So this is the x-axis that that is also located here. Same with the location of the of the z-axis. So if the z-axis is located here, the x-axis will be here, and the y-axis will be here. Okay, so I'll just give you another example. If the z-axis is located here, no, so the x-axis that we need is the x-axis here is here, and the y-axis here is here. Okay, if the z-axis is here, no, but since the z-axis is here, no, so the x-axis will be here and the y-axis will be here. So we will just measure the moment of inertia of this rectangle from the x-axis with respect to x-axis, and the moment of inertia of this rectangle, no, with respect to this y-axis, and we just sum them up to solve for the polar moment of inertia. Okay, so that's just how you do it. Okay. Okay, now for radius of gyration, it is usually denoted by the symbol K and sometimes by R, and it is defined by the relation K is equal to square root of I over A, wherein I here is the moment of inertia. So this can be X, Y, moment of inertia, or X, Y, centroidal moment of inertia, no? So it depends on the problem. And A here, no, is the cross-sectional area, or the area, the value of the area that you are considering. Okay, so the unit for radius of gyration, so this is radius, no, so this is just length, no. So as you can see here, for moment of inertia, the unit for moment of inertia is unit to the fourth power, right? So over area, so area is squared, right? Unit squared. So um unit to the fourth power over unit squared, so that will just be unit squared, right? So if you square root that, no, the square root of unit squared will be just a unit, right? So that will just be a length, no. Okay, so let's proceed now to the transfer formula for moment of inertia. So this topic, it will be very important and useful, no, if you don't want to memorize a lot of moment of inertias, no, with respect to different axes, no, or axes, no. So for transfer formula for moment of inertia, as long as you know the established x and y centroidal axis, no, you can solve for the moment of inertia of that area, no, with respect to any axis, no, to any x and y axis, no. So you will just transfer that, no. So that's just the the thing that you need to memorize here. You just have to memorize the x and y centroidal moment of inertia of some common geometric figures, no. So if you know that, no, it will be it will just be easy to you to solve for the moment of inertia of that area to any axis. Okay, so for any area, the moment of inertia with respect to any axis in the plane of the area is equal to the moment of inertia with respect to a parallel centroidal axis plus a transfer term composed of the product of the area multiplied by the square of the distance between the axes. So these are the formulas that we're going to use here, no, for transfer formula for moment of inertia. Let's say you have an area and you want to solve for and you know the and let's say you know the excentroidal moment of inertia for that area, no. If you want to solve for the moment of inertia of that area with respect to any x-axis, so this will be the formula. So this is ix equal to ix bar plus ad squared. So this is just similar if you want to solve the moment of inertia with respect to any y-axis. Okay, so this is iy is equal to iy bar plus ad squared. So in these formulas, ix bar here, this is the excentroidal moment of inertia of the area that you are considering. Okay, so this the area for that is already established, no. We have established centroidal moment of inertia or excentroidal moment of inertia. Okay, so to be able to transfer that excentroidal moment of inertia, we will need to add AB squared here. No, wherein A here is the area, no, this is the area, and then distance D or D, no, so this is the distance from the centroid of the area to the reference axis, which is the x-axis. Oh, so that is the distance D. So I'll repeat, distance D, that is the distance from the centroid of the area that you are considering to the reference axis. In this case, this is no, from the x-axis. So you will measure that distance D. Okay, for y naman, no, so distance D here will be the centroid or the distance between the centroid of the area that you're considering uh, to the y-axis. That will be the distance. Okay, so we will use this. So this formulas, no, this there is all actually a derivation for this. So let's say we have here this area. So this is our area. Okay, so if you're going to construct a differential area here, so this will be our differential area, and the excentroidal axis for this area is this is the this is that axis. Okay, so we know that the excentroidal moment of inertia, no, it can be written like this or like this, no, so they are just the same. So it can be solved by this formula, integral of y squared dA, no. So let's say that the area, no, or the moment of inertia of this area with respect to the excentroidal axis is already established. Okay, and you want to solve the moment of inertia, okay, of this area with respect to this x-axis. No, so we are going to apply our formula also, no. So for Ix, no, so this is the moment of inertia with respect to this axis, which is x-axis. So this will just be integral, no, of the moment arm. So what will be the moment arm, no, that what will be the moment arm of this area? So in this case, if this is excentroidal, this is the excentroidal moment of inertia. So if we measure this distance, no, the centroid of this differential area from this excentroidal axis, it will be y, no. So we will just name it as y. Okay, and this distance, no, from the centroid of this area, no, up to the reference x-axis, no. So this we will name it as distance d. So in short, the moment arm, no, of this area, no, with respect to the x-axis will be d plus y. So that will be the moment arm. So this will be y plus d squared dA, no. So here, what we're going to do here, okay, is simplify this, no. We are going to expand this y plus d squared. So this will become y squared plus 2dy plus d squared times dA. So if we are going to distribute this, no, so this will become integral of y squared dA plus 2d times integral of y dA plus integral of d squared dA. So in this case, integral of y squared dA, we actually know this already as the Ix sub O, or the excentroidal moment of inertia, right? So we will rewrite this as Ix bar. Okay, now here for integral, okay, of y dA. So integral of y dA, this is actually this is actually integral of y dA. That is actually the summation, okay, of the differential area, no, of the differential area times this, no, times this y. Okay, so actually in this case, no, our y is here, no. So our reference axis for this, no, so this is actually kasi moment of area. So this is moment of area, right? Moment of area, right? Moment of area, no. So if you are going to solve this, no, since we know here that the area above, no, so the area above here, no, that is equal to the area below, right? Since this is excentroidal axis. So if we are going to sum up, no, all the differential area times y, the differential area above will be positive and the differential area below, it will be negative, right? So if we sum them up, no? Because ano ha, if we measure the moment, this moment arm y, no, above, from the x-axis above, no, so that will be positive. But if it's measured below, no, from the x-axis below, so that will be negative. So if we sum them up, no, the differential area times this moment arm, no, they will just become zero, because the area above is just equal to the area below. No, so it will just be zero. No, it will just be zero. So this term will just be zero. Now for integral of d squared dA, okay, so this is differential area times ano, no, d squared. If we sum up integral of dA, no, so that will just be area lang, right? So that will just be area. So this will just be equivalent to area times d squared. No, so this is the ano, the derivation of our formula, ha. So this is where we derive this formula for ix, no? So this is ix bar plus a d squared. So this will just be the same, no? If we derive iy, no? So this will just be iy bar plus a d squared. Okay, so we are going to use these formulas, ha? So you have to memorize this. For ix, this is ix bar plus a d squared. And for iy, that will be iy bar plus a d squared. So let's solve sample problem here. So determine the moment of inertia for a rectangle of base B and depth h with respect to x-axis. So we already solved this using integration, but in this case, no, we are going to solve this using transfer formula. Okay, so if you are going to use transfer formula to solve this problem, no, so our rectangle here is has base B and has height h, no. So we know already the ano, no, the established x and y centroidal moment of inertia for a rectangle, right? For x centroidal moment of inertia, that is bh cubed over 12. Right? That is bh cubed over 12. So if we are going to measure the moment of inertia with respect to the x-axis, so our x-axis here is located here. No, so we actually know also already, no, the moment of inertia of a rectangle if the x-axis, no, is here at the base, no. So this is bh cubed over 3. So we will confirm that if that is true using transfer formula. So using transfer formula, no, so our reference axis here is at this x-axis. No, so this will be ix bar plus ad squared. So our ix bar here, this will be the x-centroidal moment of inertia of the rectangle, which is, we know that already. So that is bh cubed over 12. No, and a here, okay, a here is the area of the rectangle, which is bh, and d here, so d here is the distance, no, between the centroid of the area, which is this rectangle, to the reference axis. No, so in this case, our distance d will be this distance. So this distance is actually half of h, right? So this is h over 2. So you will square that. Okay, so our simplified form here will be bh cubed over 12 plus bh cubed over 4. So if you simplify that, that is actually bh cubed over 3. So this is ano, this is correct. No, so this is also the established x moment of inertia, no, with if the x-axis is at the base of the rectangle, no. Okay, so again, transfer formula for moment of inertia will be useful. Okay. So that concludes our discussion for this lesson. I hope that you learn the concepts. Okay, so to be able to know, no, if you learn the concept, no, please comment, no, your name, your section, okay, and the concept that you learn from this topic. No, so I hope that you are doing well, and the finals is approaching. So let's persevere, no, and press on, no, until the final day, okay, for this course. Okay, so I hope to see you soon again. So God bless you, class, and keep safe always. Bye bye.